So I thought that I had done that for you before, but I might be confusing it with the summer class. So I'm just going to do those two really quickly right now. So let's say that we have an object that is just sitting on I talked to you about how when you put something on incline, there's going to be a critical point at which it starts to move, right? So when you're just at the cusp of that point, it doesn't move. So the maximum frictional force goes from zero to that maximum, or the friction force goes from zero to that maximum as the angle increases from zero to the critical angle. And we talked about all that. I do know that we talked about how the frictional force appears, increases. Sorry, the component of gravity down the plane appears and increases as friction appears to counteract that, and it increases up to that maximum point. So let's just look at what the coefficient would be relative to all given properties if you're right at that critical point. And this is for an object that is not moving, but is, so it's static friction at the point of an object going in embankment. And the inquiry, you're going to know that, if we're going to try to write that in terms of the coefficient of friction. We have m. Now it's at an initial velocity of zero, so it's just sitting there, right? And so we're at the critical. We'll call this the critical angle, just to let us know that we're right at that point. Now, I'm not going to specify any numbers. We don't really need to do that. But whatever their numbers are, is the mass of the object and the critical angle. Okay. And of course, the initial velocity is zero. And basically the velocity is zero because it's not moving. So initial velocity, I don't want to imply that it actually is moving because it's not. So, but if it were to move, that would be the initial velocity. So I just keep that there. So, find the coefficient of friction. So the coefficient of static friction. What is that? All right. So standard operating protocol is, we take the angle, we place it perpendicular to the plane. All that should be pretty standard now, or something like this. Right here, this thing, that. Um, um, yeah, so X, Y, and so we're going to have gravity straight down, that critical angle, so straight down. So this again is over there, theta C, and of course that's theta C. I draw with the colors. And so that's going to be mg. So technically, there's just three forces, right? There's mg, there is the normal force, and then there's a frictional force. When we do the free body diagram, you just go ahead and jump right into that. We got the normal force straight up. And we're going to, with this orientation, there's always going to be mg sine theta down the plane along the x-axis, mg cosine theta along the y-axis. And then we've got the frictional, force opposite the gravity down the plane. All the accelerations are zero because it's not moving. So ax equals 0, ay equals 0. This is a static case. So we'll call this Fs just to imply that it's static friction. So now moving. So how can we figure out the coefficient of friction in terms of given quantities? Well, you apply Newton's laws for both the x and y direction. So in the x direction, so force in the x direction equals 0. Fs out the plane. So that's mg sine theta critical minus F equals 0. I don't know what F is, but I'm trying to find mu S, so I have to write that in terms of F in terms of mu, Fs in terms of mu, and so I use the definition of friction, mu S n. Okay, so then putting that in, then I'm going to get mg sine of theta critical minus mu S n equals 0. Okay, I don't know the normal force, but I just leave it at that for now. Yes, so it's two unknowns there. Sorry, the two unknowns are going to be mu s and n. So I at least need two other equations. Technically, there are four unknowns. The four unknowns are the normal force, the frictional force, the coefficient of friction, and no, I'm sorry, the three unknowns, F, mu s, and n. So we need three equations. We've got two of them. Newton's law in the x direction, definition of friction, and the third one is going to be Newton's law in the y direction. So that should be equally determined, and we should be able to find whatever we need. So that's how you know you haven't missed anything if you're equally determined. So you want to check that. And so the last thing is the sum of the forces in the y direction. Ay is equal to 0, so it's the first law. So the net force in the y direction equals 0. What forces are there? Normal force up, mg cosine theta down. So I get normal force minus mg cosine theta equals 0. There's only one unknown there, that's n, and that's it. That gives me my unknown I can solve right here. So I solve it and then stick that solution into 4. And the result that I get, 7, is that n is equal to basically mg times the cosine of theta. Okay, so now I'll put that in here. So 7 into 4 yields mg sine theta and I keep kind of losing that critical quotation on there. So minus mu s mg cosine theta equals 0, and solve. That's so the only unknown now I've eliminated. I have eliminated all the other unknowns, namely f and n, in terms of in favor of mu. So I solve for mu. You can see that the mg's are going to go out. That goes, and then I get that mu s is going to be equal, take the sine over, so sine of theta, and it'd be minus, well, minus mu s cosine of theta c equal to minus sine theta c. So therefore, mu s equals sine theta critical over cosine of theta critical equals mu s equals the tangent of theta critical. So that's the thing that's kind of a classic result, in that you would think that the tangent of that mu is going to be dependent upon, the material somehow, some function of that. But for these kind of mechanical macroscopic considerations of problems, it's really the geometrical situation in which you're, you know, in which the forces are interacting that ultimately determine the coefficient. And even when the angle is zero, because you'd say, well, there's no coefficient, there's no frictional force, whenever the angle is zero. But when the angle is zero, that also works out because the tangent of zero is zero. So it's still kind of dependent upon that. It's just zero, right? Because the coefficient is zero, so that's why the frictional force goes out in a way. I mean, but there's still consistent with the dependence that this equation implies. So what we can say is that the frictional force, what I like to say is that friction is a purely geometric quantity. It does not depend, like when you look at this equation, the definition of friction, if you were to solve this from US, right, US is equal to friction over the normal force. If you just consider that equation, it looks like friction is, well, it is a constant of proportionality between the normal force and friction. That's true, because you can do that when you do those experiments and you graph them, you can see that. But that doesn't necessarily, so this equation means that friction depends on the normal force, but it also seems to imply that the coefficient of friction is proportional to friction and inversely proportional to the normal force. It's absolutely not true. It doesn't depend on either one of them. And that's what's not so obvious. That's what's counterintuitive. It just happens to be a constant of proportionality between the dependence of the normal force and the friction. And these things do definitely depend on one another, right? When you increase the normal force, you increase the friction. And the friction is a reflection of the normal force, so back and forth. But coefficient is not dependent on either one, as this equation implies. And so there's several concepts over the course of physics where that'll be the case. And actually, whenever you have a whenever you have a relationship or a definition, something like that possibly would be the case, where some or all or some constant of proportionality will not actually be dependent on what it looks like it's dependent upon. There are several times in physics where you're going to account where we will encounter that. This is the first, but we'll see it again next semester with various concepts: capacitance, um, inductance, resistance. When you look at Ohm's law, um, yeah, those are just a few that strike come to mind. So what we say is that coefficient, the language that's I like to use and that is used more so for those other concepts, but it's also for this as well. That because of what comes out, but friction is a purely geometric quantity. Sorry, coefficient of friction, not friction. Friction implies the force. The coefficient of friction is a purely geometric quantity. Okay. Now I'm going to let you repeat the problem, and but do it for an object sliding down at constant velocity, right? I told you that when you're at the critical point and you go to a higher angle, ultimately the motion will always be accelerated motion. But if I were to then drop the angle once it starts to move, or better yet, I could get it to a lesser angle, drop it below the critical point and then touch it, and so that it slides down at a constant speed. I think I tried to dramatize that for you. That's also a situation where all the accelerations are going to be zero. So you can prove that to yourself, really, that you're going to get the same result, except that, in fact, I said critical angle. I should probably go back and make this, because there's two critical angles, one where it moves at a constant velocity down the plane and one where it's just right at the point where the acceleration is zero. So a better way to label this angle would be, let's have a friction Fs for static friction, have mu s for coefficient of static friction. I should make this a theta s for the angle, the maximum angle where the friction is zero. And by the way, this was also misnamed. For static friction, it's less than or equal to. So I have to throw that guy in there. And three equal signs means it's a definition. So I guess the way I did it in my notes is that when I define friction, I did make it kinetic, and there three defined as a coefficient of friction times the normal force in general. So we have that, but then when we make it specific to the static or kinetic friction force, this is the relationship for static. I guess the the other way around. So the friction force is less than or equal to this value. So less than or equal to, and yeah, friction is just going to be it's just equal to. And so what I'm where the mass is actually sliding down where the velocity is a constant, and you do have, yeah, and so again ay and a x are zero. Ax equals zero, ay equals zero. Obviously ay is zero because it's not moving on the y-axis, but if it's moving down at a constant velocity, ax is zero. So you'll have a similar situation that looks like this, but the frictional force will be a kinetic frictional force up the plane. So you'll have F K up the plane, and we'll just go ahead and write it mg sine theta k down the plane, and mg cosine theta k down the plane, and of course the normal force up the plane. Just jump right to the free body diagram on top of that, where this angle here is now theta k, and but then if I have this being my component, grab my total gravitational force straight down, then of course that angle here is now, the critical angle becomes a theta k. So because the components and everything are going to be the same mathematically, it literally is the same derivation I just gave you here, except that every place you have a static friction component or something, it will be kinetic. And in the end, you should see that your answer is going to be that mu k is equal to tangent of theta k. So that's something that I probably should have done for you before doing that more complex problem. Because what happened is when I got the answer, and go back and look at it, it was the last thing that we did. What I was checking to see is that as complicated as it seemed, it did actually reduce to this. Remember, we had the car going, it looked kind of like this, but the car was going around the bank track. And I was like, at what velocity, at what thing should it, what would be if I have a set radius and constant speed, what is the coefficient of friction? Is the coefficient of friction in terms of given quantities v, m, and theta and all that. And so it turned out, I can't remember what it was, but it was kind of a complex thing. But it turned out that um, for that same problem, you could say, like, what is the angle at which the car just sits on the embankment, right? And at the critical angle. And so where the velocity is zero. So it turned out that it reduced down to tangent theta. But obviously, if it has a velocity, well, actually, to be honest with you, the angle would change, given if you, yeah. But for a specific value of velocity, the angle would be constant. Yeah. So yeah. Anyway, it reduced back to these solutions. So that's what I was alluding to, and thought that I had done that explicitly for you in class, which I'm not sure that I had done. Now I have, and you can go back and take a look at that solution. Yeah. Let's see here. So we can do more problems with this. Other kinds of problems that with centripetal force. There's kind of a set of problems that I like to do as well. That's related to what I just did, but looking, the coefficient of friction, and you're looking for the velocity. Like, at what velocity will the object, be at a certain radius? I think that was one of the first ones I did with you when I had the mass and I was twirling it around. I think that's the problem that I asked you. What for a given speed, what is the angle, or for an angle, what's the speed? So typically that's what I like to ask, is what, given theta, m, theta constant, m constant, the radius constant, what speed would keep it at that particular radii, keep it from slipping up or down, or just at that particular radii. So maybe we can do a couple like that. I think that's worthwhile. All these things just give you practice and over again, just being able to set up Newton's laws correctly and solve for whatever unknown is being asked for. It's kind of then you get to a point where you just become very versatile at applying Newton's laws appropriately, and a lot of implications of things that may not be obvious to you, may be going through the motions, but the more you do it, the less it's just going through the motions, and the more you're actually thinking about what you're doing, and implications come out, and then it starts to bake in. So maybe this one would be good, where we go back and do this with the car, with the car on the track. But as opposed to looking for the coefficient, in that case, let's assume we know the coefficient, and let's find what speed it would be, you know, it would be such that it didn't slip up or down. That'll give me an opportunity to do that problem again, because I think I got a little turned around, and so I had to, the presentation wasn't as smooth. Got a little lost or something. I forgot what I was doing, or something happened. Okay, so race car again. Race car on a bank. Banked. Okay. So again, this is the setup. We're looking kind of the velocity of the car is coming. Sorry, it doesn't look like a car very much, but it's coming. So the car is doing this, and the radius of the track is going to be something like there's some center, here that's going around. Right? So it's doing this kind of situation. We can make it a circle. I don't know, whatever. That doesn't matter. At this point, it's taking an instant shot in time, and we want to know. Yeah, I guess we could. If I make a radius, then we can assume it's circular. Let's just go ahead and do that. Simple assumption. So at this point, the velocity vector is coming out toward me, and I'm going to draw velocity over here somewhere. Just so I guess I can make it a different color, but I'll make the forces a different color. I'm going to go through and talk about various things that we talked about because they still apply. There is if it's coming like this, and the velocity is coming out toward us, then there's a kinetic frictional force directly back. That's not something that's going to come into play in what we need because of reasons I mentioned again in a minute. So there's a kinetic frictional force that's directly into the board. Now, again, I'm going to do something a little bit weird. Normally, we make the horizontal axis horizontal. That's because if something is slipping down or up, it's going to slip along the plane. Now, this will do that if it doesn't, but we're assuming it doesn't slip. So we're saying at what speed must it be such that it doesn't slip? And also something else I'm going to do for you, I'm going to make this a simple problem first. I'm going to make it so that there is no coefficient of friction. So let's first do the problem where the coefficient of friction is 0. It's a frictionless surface and the thing is going around. I know that's a little bit weird because if it's frictionless, how is it rolling? Whatever, it's theoretical, right? So maybe it's got a jetpack on it or something. And so that's how it's moving around. Point is, it's on this embankment. We're moving at a constant velocity, a sustained constant velocity. So what radius and the thing that's not changing is the radius r and the angle of the plane angle theta. But what must the speed of that? And so we know it's experiencing centripetal acceleration, it's centripetal velocity. So what speed must it be such that nothing changes? There's no slipping up or down, so that theta changes, and in fact, r would change as well. So if we're experiencing centripetal acceleration, that means with no slipping, that means that there is no component of acceleration along the plane or in the y direction. However, there is a component of there is an acceleration in a direction that's horizontal to the ground. And that's centripetal acceleration. It's always points toward the center of the circle, right? That the thing is mapping out. So there is an AC in that direction. So that's what dictates to me that I'm going to shift the axis back to a more conventional axis where it's actually parallel to the ground, because in doing so, I'm going to have a angle. I'm going to have a coordinate component that is parallel to the acceleration, which is, I always want that. If I don't have that, the problem, as I've told you several times, complicates. Because then I would have to have my acceleration, find the components of my acceleration along with the forces. And that it makes it difficult. I think it makes it transcendental, meaning you can't actually solve it analytically. You have to solve it numerically because there's no way to uncouple the angles from both sides. And you've just done that needlessly. It's not that it's an inherent transcendental problem. It's just that you set up the mathematics. It's kind of like saying, why don't we go put our axes on the moon for this problem? We could do that. There's nothing and if we did everything mathematically correct, we should get the same, there'll be the same numbers no matter what axis you took. Otherwise, Newton's law, as long as, excuse me, actually, that's not true. Just screwed up. Yeah, it's not true. I guess it's not true because you have to have, there's a caveat that you can choose whatever coordinate system you want, but it has to be an inertial reference frame, which is something I haven't defined for you yet, I don't think. I do that in in the next chapter or next, when we get to work. And this is, yeah, we haven't done that yet. So an inertial reference frame is one that actually does not accelerate relative to other objects or other reference, So if I did put it on the moon, knowing that the moon goes around in a circle, even though it goes at a constant speed, assuming, circular orbits and stuff, it's still not constant. The direction is changing. It's experiencing its own centripetal force relative to the Earth. Acceleration. So that would be considered a non-inertial reference frame. It still where the moon is, and even though the moon that is still at that point, in that case, it would be good. And use your coordinate system so that an acceleration is in a direction of one of your axes, and you're good, and it makes the mathematics easier. So then you're only finding the components of forces, the left side of Newton's laws as we write them, as opposed to the motion side. So that's what's dictating that. That's what's driving that determination. Now, having said that, it changes things up a little bit because normally we have to find a component of gravity, but now we don't. So mg is actually here. Mg is here. Now the normal force is going to be at an angle relative to our coordinate axis. The normal force, again, is perpendicular to the surface of this plane. Perpendicular. So the normal force is going to look something like this. So now I have to resolve that relative to my axis. And the frictional force, which is parallel to the x-axis in the opposite direction, is also going to have components. Also going to have components. And the components will be, well, the frictional force is up the plane. Oh, but I said this was frictionless, isn't it? Okay, yeah. So that's for the next step. In this case, if we're saying during the frictionless case, where we consider mu zero, then we're good. We just have those 2 points. Let's go ahead and do this real quick, and then we'll do the more complex. So assuming mu is 0, there is no friction. And so we basically just have to resolve the normal force. Now, again, you have to kind of go through and prove what's there for yourself. You have to do your little geometric exercise. I'll do that with you here. So, and I forget the names of these laws, or no, not laws, but properties. But I don't remember the names, but I remember the properties. So, and for me, it's baked in intuitively, so I don't have to go through and call them. But look, this is a right triangle. So that if that's theta, then this guy is the complement of theta. I'm going to make that, yeah, if this is theta, let's just say beta is the complement. So that's beta, right? Because this is 90 degrees. So if that's beta, this is beta. So that's, yeah, that's beta. So, and this is the x-axis. So I guess how can I get there? I guess I can do that. Yeah, I can drop down the perpendicular from the rear. So I make a, yeah, okay. Kind of getting messy because of but if I do a line of action here, with my normal force like that, then I've got a little right triangle right here. Let's do it in green, that guy. So where that's 90 degrees. So if that's beta, then this inside guy is also beta, But then this guy is theta again. And if that's theta, then that means this is theta. So when I do my free body diagram, I'm going to have straight up, that's going to be, if this is theta, it's the adjacent side. So this is going to be n times cosine of theta straight up along my x-axis, this guy here, right, and at this right triangle. So that's n times the sine of theta here. N times the sine of theta. And mg is straight down. Maybe I should have made my body diagram all black, but that's what I've been normally doing, but okay. Mg. Now keeping in mind the centripetal force is still, the centripetal acceleration is still pointing in the x direction. Now keep it, I guess I do have the force on there. Again, I still have this kinetic friction force that's into the board, effect option for centripetal. And that's straight out. So I should put that over here. So I should say like F applied for the engine. Those forces, they're there, but they're not affecting me, the motion for the coordinate directions that I'm considering. So an applied force is out of the board. And if there's no, if it's moving along at a constant speed, that means that in the z direction, which be straight out of the board, F applied is along the positive z and Fk is along the negative z. They're equal and opposite, so that the acceleration along the z direction is 0. And that's why it's going at a constant velocity or a constant speed around. And at this instant, that speed is pointing straight out at us. Not constant velocity because the direction is changing, excuse me, constant speed. So those forces are there, but I'm not going to put them on my free body diagram because it's just messy. I've got it over here. I've acknowledged it. It's not going to affect anything here. And this is an interesting thing because I showed you that it's the same surfaces. So when we do actually have friction, well, it's frictionless, I guess. So I guess technically, yeah. So that's a good point. If it's frictionless, I'm going to be moving at constant speed. That's a good point. You didn't make, but I didn't. If this thing actually isn't here, technically it isn't. Only when we have friction. So I'm not racist, but just for now, we'd have to consider air. That, and also it can't be, like a standard car. It'd have to be moving with some sort of, I don't know, because you need friction in order for the tires to roll. So again, it's theoretical, but you would have to, I don't know, maybe have some sort of, it's a tour or something, or you got like a meaning that there's some jetpack on the thing. Something has got to be making go around, but whatever. Let's just do the theoretical thing, and then we're going to do friction, and we don't have that problem anymore. For theoretically speaking, then what are we looking for? The speed at which it stays on that track and doesn't slip or slide or whatever. And given, what is given is the mass and the angle. So what's given is m and theta. Okay, we just apply Newton's laws to this guy. And we can start with the first law along the y direction where ay is 0. I'm just going to write it. Well, I'll keep it up for you. So the net force in the y direction equals 0. So then in cosine theta up minus mg equals 0, so that n equals mg over cos theta. And it's just, since there's no friction, of course, that's just information that we'll need when we get friction. But and then in the x direction, we have basically n sine theta is equal to AC, and that's it. So in the x direction, net force equals mass times the acceleration. That's the centripetal acceleration. So the force is going to just be mg sine theta. So mg sine theta equals mac. But remember, AC is equal to v squared over r. So then mg sine theta equals mv squared over r. And there we have the one unknown. We can solve for the velocity. The mass goes out here and here. And we're finally left with so g sine theta equals v squared over r. And so solving for r, for v, we get that the velocity is such that this thing will not slip is going to be equal to g times r times sine of theta, and we take the square root of that. So it's not dependent on the mass. How about that? Just dependent upon the angle and the radius. That's it. So that's the speed with no friction at which it will stay on the plane and not slip up or down and just go around. Everybody's kind of quiet today, just making sure everybody's there. Can you hear me? Everybody's there. You can hear me all right, and all the stuff is making sense. Kadeem, are you there? Mikey, anybody?
We can hear you, but it's kind of laggy though. At least for me, it is. So it's like at like some points, it's kind of hard to understand.
Oh, really? Let me so okay. Yeah, I did see kind of a lag on this camera. I don't know what's going on with this. Maybe I could I don't know, I'm gonna mess up something. Oh, the chat.
I think you can use your computer as your camera because it's like it has a little worse quality, but it's not laggy for me at least.
Okay, I mean, well, it's there. I mean, you mean for I don't know what so it's there. Like there are three cameras, so you can look through either one, whatever one you want. But for the sound, you mean? Okay, yeah, I guess I could do that too. So let's switch over to that. So which one is this? So let me. Yeah, okay. Disconnect that guy. So connect here. I wonder if that's what actually was happening. But no, I can't be for that. Speak it off. Okay. Speaker there. And here. Cut off the speaker here. And then make this guy. You can still pin one or the other. Testing. Testing. Testing.
It works.
Okay. Okay. And this one to the screen. So you don't get any feedback or anything like that?
No.
All right, cool. All right. Yeah.
Oh, Professor, I had a question actually before we
Yes.
go on. This might be kind of a dumb question. Why is the normal force
Stop saying
not
that.
okay?
No questions, dumb questions. Don't say you say it a lot. Don't say it anymore, ever.
All
In
right,
this class.
all right. Well, like, why is the normal force not like how? Shoot, sorry, I'm trying to like choose how I word this. Like, how come the normal force doesn't like form like a 90-degree angle with the axis at choice?
Good, because it's not normal to the axis, it's normal to the surface. That's where it's getting its name from. It's always normal to the surface where and I guess I kind of drew it's a little bit yeah, because it's a little bit off from how I drew the thing with the car and stuff. It's just, let me redraw it over here because it looks like there's a couple different angles there going on. Let me draw a little better. Because I was going to do that again anyway. Now that we're going to do the one with friction, that may or may not be what's confusing you. I'm not sure. I just saw that. I'm making my axis like this. Right up and down like that. So the normal force, it's actually got to be a better way to draw. It's like it's going to go through the car, but it's like this. It's not at an angle relative to the car, which I drew over there. So both the wheels of the car, like they're making they would make a 90-degree angle with the surface. So just like the edges of the tire make a 90-degree angle with the surface, everything's making a 90-degree angle. Like if I look at the edge of the car over here, that's 90 degrees with respect to the horizontal. So now the normal force is consistent with that. So it's normal to the surface of contact. So over here, I kind of was off because how the car is a little slanted a little bit. It should be more like that. So I don't know if that's what was also what was throwing you off or not, but this is better. Now, if that's not what was throwing you off, what was throwing you off is why isn't the normal force like this? Like along the positive y-axis. That's a different question. That question is because I'm choosing my axis so that it's not. Are you through here? I can't.
Yeah,
Did you say
yeah.
something?
No,
Oh.
no, I'm just like listening.
I'm getting some feedback somewhere, and I don't know why. I think it's with my phone, but it's so quiet. I mean, right down, it says I'm not using it. I don't know what's happening with it. I think it's volume cannot be lowered to 0 due to iOS system limitations. Okay, something's going on with that whole connection thing. I'm not sure what it is, but I can hear a little. Oh, I can hear a little feedback over there. Disconnect. The volume cannot be okay. I'm not sure what's going on with my phone now that it's not the main thing, but if y'all can't hear that, that's fine. So I'm sorry. What'd you say, Mikey?
I was listening to you. Like I didn't say anything.
Oh,
Yeah.
so does that the question? Why isn't the normal force like this?
It was kind of like I guess both.
Okay.
Yeah. So I was confused why it wasn't like, I guess, parallel with the y-axis or like along that a y-axis, and then I was
Mhm.
also just confused like what like the normal force was like, what I guess it was like associated with. So
Yeah, it's associated with basically the tires.
okay.
That's where the friction is, right? It's like that's what's touching the surface. So if you look at the surface, you know, the surface, it's normal means that where the two surfaces, the road and the bottom of the tire, those are the contact surfaces. The normal force press it's perpendicular to that plane along which the plane of contact is. So like the plane of contact is the bottom surface, but the ground is pushing up on the tires, so that up is perpendicular to that contact. And the tires are pushing down through the surface of the road, but that would be, you know, perpendicular to the plane of the contact surfaces between the tire and the road. So normal, as always defined, is defined relative to the surface of contact. For a conventional, when we're not dealing with centripetal acceleration, like with that block just sitting there on the tabletop there, it could possibly move. It could possibly move. And if it moved, it would move down the plane. So that's why even when it doesn't move, I still choose my axis to be the x-axis to be parallel to the plane. In which case, the y-axis then has to be perpendicular to the x-axis, and the y-axis itself is perpendicular to the plane. So whenever you draw in a normal force, it just so happens that they are together. It's kind of like I've just in this problem here, I've just taken my axis and shifted it through an angle, a theta, the angle theta being the plane angle. That's all. Why do I do that? Because in this case, it's not slipping. So there's no chance that it's going to go up and down the plane along the x y axis, but it does have an acceleration if it's moving in a circle that is along the horizontal relative to the ground. So I shifted my axis so that I could have that x-axis parallel to that acceleration, namely the centripetal acceleration. So that's what's the difference in these problems, and that's why I did it. Does that make sense?
Yeah, it does.
Yeah. Yeah. So let's continue then and like make mu not zero anymore, and let's do the problem again and see how that changes, how that's going to change this solution, because this is now the kind of the base solution for velocity. Now something actually really interesting happens once you throw friction in, just by throwing it in. And I have to explain that to you because I don't want you to mess up. So now, yeah. So I've got my weight is going to still be straight down. So mg. Now, how should I draw the frictional force? If it slips, if it's so now we don't want any slipping. So if we don't want any slipping, then when we're at the critical point of slipping, we know that the frictional force has to be opposite that direction. So in this case, let's go with you, Mikey. What would be the direction of my frictional force um, for this object now? Now that mu, and we'll assume that there's no slipping, so we'll call it a coefficient of static friction. And again, as I mentioned, we always have kinetic into the board or out of the board if it's going the opposite direction, but I'm talking about the static frictional force that keeps it from slipping up or down the plane. So where would I place it here and why? That vector.
Well, but wouldn't it just like, I thought it just depended on like which way the car would be slipping.
It does. Good. Very good. So that's my point. it could slip two ways, not just one way. So you make a choice, and we'll do that one first.
Okay, so let's say if the car is slipping down the plane, then the frictional force would have to be up the plane.
Good. Good. Now let's think about what Mikey just said. I agree with what you just said, but there's other implications here. If it's slipping down if it's about to slip down the plane, and we're at that critical point, can you tell me how the magnitude of that speed that it would have compares to if it were about to slip up the plane, Mikey?
Wait, sorry, can you repeat that? Like,
Yeah.
I get that.
So it's going around the track and it's about to slip down the plane. Like at this point, it's about to slip down the plane. But you also implied that it could slip up the plane. So if you consider the speed that it has, actually it's going around like this. Sorry, the speed but it's one that slips down like that. It's likely to slip down the plane, at some particular speed. We're going around like this. If you compare the speed that it has when it's about to slip down the plane to the speed that it would have if it were about to slip up the plane, how would those speeds compare?
I see.
Yeah.
Okay. It's an interesting question. I would
Well, let me ask you this: would it be the same speed?
I want to say it's not the same speed, but I can't find a reason as to why it wouldn't be. But my intuition tells me that the speeds would be different. So,
Okay.
I'm trying to think if it's has to do anything with the frictional forces.
Let's just go with your intuition more than trying to analyze. Let's look at this scenario. This is something we've all done. Actually, let me do this, guy. So I'm swirling this thing around, and my speed is constant, which means that the angle is constant and the radius. Now, the radius is the perpendicular distance, the L sine theta. We've done that, right? Like it's this distance from the vertical to where it's out. So that's the R and the theta that's similar in this problem, okay? So right now, V is constant, and if V is constant, the R distance is constant, and the angle relative to the vertical is constant. Got that?
Yeah.
All right. How is the speed going to compare to this speed if I want to make the thing rotate at a higher angle and a larger radius? Would it be less, equal, or greater?
The speed would be greater.
Yeah. If I make the thing speed up, you can see it's going to start to spin, at a larger angle and a larger radius. Good. Now, if I go back to that same speed, if I want to make it go, if I want to decrease R and decrease the vertical angle, how would the speed of that angle compare to what it is right now at this constant speed?
It'd be slower if it
Yes. It would be slower. So if it slows down, you can see that the vertical angle decreases and the R sine theta, because theta decreases, R sine theta or L sine theta decreases. Okay. So you see, let me just point something out also there. When you were trying to analyze this problem, so we literally have two ways of thinking about the universe. Like this is psychology, right? Your left brain and right brain. Now I know we kind of exaggerate that in popular culture, like right brain people are artists and left brain people are, it's not that cut and dry, but the cognitive abilities of the left and right hemispheres are different. The difference is in how you were trying to describe this. You said you didn't know how to, why. You felt it would be different, but you didn't know why, because you're focused on your left brain trying to figure out the equations. We don't know that. That's what we're trying to do here. You can't solve a problem before you solve it. That's actually what you're trying to do. But if you switch to your right brain or think of a thought experiment where maybe you don't know the quantitative aspects of it, because literally that's, again, what we're trying to figure out here. So you can't solve this thing before you solve it. But there are things you can understand about it if you shift your perspective to a different way of looking at it. And your intuition, right brain abilities, are coming up with some thought experiment that's similar to this, where at least, even if you don't understand quantitatively the relationships of the quantities, you do understand, maybe demonstratively or intuitively, based on experiences that you have with what objects, how these quantities relate from your practical, or I would say empirical experience, empirical being your experience of observation with things like that. In that context, you got it right out. So you did know it, right? You know that it has to be a larger speed for a larger radius, and lower speed for a lower radius and angle. Okay. So when you take that and apply it back to this situation in the context of the question that I asked you, how does the speed of the car compare when it slips down the plane or is about to, as opposed to when it slips up the plane? Now answer the question, Mikey.
So when it slips down the plane, the speed would decrease, but if it slips up, then it increase.
Yes. So those speeds compare. The speed that slips down the plane is less than that slips up the plane. Now, if that's true, but first of all, let's just point that out. And it's not just for you, it's for everybody. That's what, when I talk about the difference between left and right brains and cognitive reasoning, that's a kind of a qualitative example of what I mean. They are different. So as you become self-aware of that, there probably are things that you know, but you might not be aware that you know them because you're thinking in a certain perspective and not thinking about other perspectives that might be easier for you to grasp. Okay, so just keep that in mind. Now, back to this problem. So basically what we're saying is below a minimum or above a minimum velocity, it doesn't slip. And below a maximum velocity, it does not slip. If you go below that minimum velocity, it slips. If you go above the maximum velocity, it slips. Well, doesn't that imply that there are a range of speed, every speed between the minimum and maximum, it won't slip? Yes, it does. Unlike this scenario, where as soon as I start to change the speed, the radius changes, right? It's going at a constant velocity, say it's 5.0 meters per second. If I go 5.01 meters per second, even though it might not be noticeable, this radius changed. Yes. With this scenario, that's not the case. I'm at the minimum speed, I start to speed up, nothing happens. It doesn't move at all. And it goes to some maximum range such that if I go above that, then it slips. So just by adding in friction, I go from one, because this scenario here is more like the one that I was twirling it around, where there's only one velocity. Basically, the minimum and the maximum are the same thing. And so there's only one speed, sorry, not velocity, speed. So that if I change the speed, it slips up or down, just like with the thing twirling here. But in this case, with friction, there's going to be a range of velocities. Now, what I'm going to do for this problem is I'm going to calculate those, basically that range of speeds. I keep saying velocities, range of speeds. But it also implies that the periods are different. There's a range of periods, basically. There's a minimum period. Remember, period is the time it takes to go around, because the speeds are changing. So there's a minimum period that it won't slip going around the track, and a maximum period. And they're flipped. The minimum period goes with the maximum speed, and the maximum period goes with the minimum speed. So there becomes a whole class of problems of things twirling around, like moving around on surfaces, where that's going to be the case. And I like to kind of explore that, kind of like with blocks on the plane. I like to do that. There's all kinds of scenarios of problems where you can do the frictionless case and get, whatever the kind of base value of the speed and period, and then you can get, throw friction in, and and you get, a range of speeds. There might be a problem. I mean, they usually do a classic problem, a cone problem in your book that kind of feeds on this kind of that is related to this kind of problem. Let me see if I can find it. I mean, I don't know if Halliday and Resnick has it in there. But let's take a look at your book and go to that chapter. Go to the back of the book. It's usually like in the problems. It's a more advanced problem, but there might be a couple of them. Go to the problems, and this is going to be applications, chapter 6. And we'll go down to problems. And this is uniform circle motions. This is where it's talking about that use of theory and all kinds of things. Oh, that's a good problem to do. I want to take a look at that. I mean, there's a whole bunch of problems, this kind of stuff. Let's just jump down to the problems. Go jump in. So let's go down to the. Oh, that's interesting there. This thing, I think, did we look at that? Well, there's this desert where the stones drag along, and the people say that it's wind. I got to tell you, man, you might want to read that. I saw this on this story. This is one of these deserts. I think it's in Brazil, where these big heavy stones drag along, and the people say that it's the wind that's doing it. I mean, there's so much about that just feels like a crock BS to me, but that people are just making, because I don't buy it. Because if it were the wind, why such a straight line? The wind doesn't blow the same direction all the time. And even if it were a constant, like a superposition of different directions, still, why does it? The superposition of the wind blowing on this thing ultimately is going to blow it these lines are perfectly straight lines, and they're always perfectly straight lines. I don't know. I have to look at that myself. But anyway, that's interesting. You can Google it, or maybe might read that. But what they're going to tell you is that it's the wind doing it. And yeah. And so what we're seeing here is a frictional force, drag frictional force, but I don't buy it. I don't buy that. Anyway, that's a kind of a diversion. Let's go down and see if I can find some of these problems I'm talking about with centripetal force. Actually, let's go ahead. Make it a little bit bigger. Here, you're starting. So, like, this is a good problem. 57. Sometimes I do variations of that. So you can have that. You can put that on a plane, the top mass, or you can put the bottom mass on an incline at an angle. Sometimes I do both. So that's a nice one. Puck on and just start with the frictionless surface. And basically it's saying that this puck is twirling around, and it's twirling around with centripetal force and putting a tension on the string such that the bottom mass doesn't drop down. So that's a nice one to then put that small mass on a incline, like the race car we're doing here, at a certain angle, and see how it changes. That's a nice one. And then you can put, as I said, you can put the bottom one on an angle too, and just, this is also kind of a related problem, but it's with tension. It's not on the surface. So that's a nice one. And maybe, tweak it around. A couple others. Well, that one I did in class. So that's the oscillating pendulum. We did that one. This might actually be the one we're doing now with, or just sliding down. Let's see. This is 650 to 73. Coefficient for kinetic friction between a block and incline angle is the magnitude of the. Oh, that's just sliding straight down. So it's not going in a circle. So that's not. We've done that one too. All of these, any of these are good. All of these with the pictures, that's kind of what I do. Go through and work through one of the problems with the pictures. Box acceleration, that's slipping straight up and down. So that's not centripetal motion. Let's get that. Wait a minute, what? Is that it? Okay, so they don't have the one I was thinking about here. That's the end of the chapter. Is it? Guess so. But they might find it in there. Maybe there's one in there like what I'm thinking, where there's something twirling, but they just don't have a picture with it. You go through and look through. but it doesn't look like it. Okay. Doesn't look like it. All right. Well, what time is it? Oh, we went past the break. Well, okay. So let's take a break right now. We'll make it a working break. And let's just, so you have to do these problems separately. If you want to find, so this is going to give us the minimum speed and the maximum period. If you then want to find the maximum speed, you have to go back and make the frictional force down the plane and do the whole problem again. So it's worthwhile for me to do these in class. So let's go ahead and crank this out. So yeah, remember that. What do we remember? We want to remember that. What am I saying? Oh yeah, so this is going to be for the minimum Vmin, determine Vmin and period max. Okay. And basically go through and do what we just said. Like, so you have a basis here. So now you just have to add in friction, find its components, and then go through and solve. And then in the end, oh, and by the way, the period here, let's go ahead and do the period for this guy, because this will give you something to compare to. Now, how do we get the period? Well, the velocity is just equal to total distance divided by total time. Well, the total distance is the circumference, 2 pi times the radius, and the total time is the period. So then the period will be equal to 2 pi r times the inverse of the speed. So I can go ahead and crank that out. If I take this and put it down inside here, I'm going to have the period, let's keep it going, 10, 11. So the period then is going to be equal to 2 pi times r over the square root of g r sine theta. Okay. Well, if I want to, how do I can simplify that even further. I can make, if I make this an r squared and then take the square root, basically r is equal to the square root of r squared. So I could say like period is equal to 2 pi times r squared over g r sine theta, right? Because if I make it r squared, I can then just incorporate it under the same radical. And then what I have is g r squared goes into r1, r squared goes into, sorry, r goes in r once, r goes in r squared once, and I'm left with 1. So then the period for no friction is going to be 2 pi times basically the square root of r over g times the sine of theta. Okay. So I can compare that guy to, so I can compare both these answers, the min and max period. So this value should decrease somehow, and this value should increase somehow. So we'll see that come out in the analytical solution. And of course, when I have V max and V min, then this should increase and this should decrease relative to those values. So yeah. So let's have a working break. Go ahead and do that. And we'll then compare them.
Professor, what does this say in equation 12? It's kind of blurry for me. Say
Yeah.
like 2 pi square root, is that r in the numerator?
Yeah, it's r squared. So what I did was,
okay.
I said I made this r is equal to the square root of r squared. So I'll just let you cancel it out. So then if this becomes r squared over g times r sine theta. All right. Yeah, this is 4 class periods on Newton's law. That's probably worth it in applications. This is foundational. Let's make a working break, and so see if you can get the solution here for this, and we'll take it. Come back in about 15 minutes or so. Maybe do the next one as well. See what you got. Well, if you look at it from this point of view again, this is prove it for yourselves that if the plane angle is theta here, then that means that this is going to be theta. And I think so is that's 90 degrees. So this is also theta right here. Yeah. So here we will have basically n sine of theta. Here, n cosine of theta. But then for fs, it's going to be the sine of f is going to be along the y-axis, right? Because this is theta, so that's the opposite side over here. That guy, fs sine of theta, and then we have this guy here is fs cosine of theta. That starts to get a little bit interesting. If we do the free body diagram, I'll do it down here. And it's nice because we could just have the regular horizontal, vertical and horizontal axes. So here we're going to have an n cosine of theta and an f s sine of theta. Along that direction, we have n sine of theta. But then back here, we have f s cosine of theta, and then mg straight down. Also keep in mind that ay is 0. Ay is equal to 0, but ax is equal to v squared over r. It's non-zero. So let's do y first, because that's the first law. So the first law is net force equals 0. So what do we have? N cos theta plus fs sine theta minus mg equals 0. I'm going to go ahead and put in the mu-s thing for, and I guess what we're looking for, we're looking for the speed. So we're assuming that the mu is non-zero. So basically, for this scenario now, what's given is we're going back and we're saying that we have m, theta, and mu-s. Those are given. So then this becomes n cos theta plus mu-s n sine theta minus mg. Now, you know, sometimes people are still, even at this point, are still tempted to put in an mg for n, but you don't know that. You actually get that from this equation. We're going to solve that here to see what n is, so you can't just throw that in. And the two unknowns are now n, and well, actually, no. There's only one unknown because we know mu s, a different problem than we did before. The only unknown is n, and so now this is going to show us what n is. We factor it out, and I'm just going to go ahead and do it in one step. Factor it out, you're going to have cosine mu s sine theta minus mg and times n minus mg. So n is going to be equal to take mg over mg, and then this becomes cosine of theta plus mu s sine of theta. So that tells me the normal force now for this guy. Compare that back to, I've erased it already, but previously the normal force was just, I think it was mg over cos theta. Yeah. And it reduces back to that when mu s is 0. So the previous problem was with mu s, you know, frictionless. Mu s is equal to 0. So sure, and mu s is equal to 0. Normal force goes back to be what it was before, which is mg over cos theta. So again, that's, you know, verified. It's giving us what we expect. Oh. Now let's go into the x direction. In the x direction, we've got so we're along this direction here, and so here. And so basically, which force is greater, n sine theta or f cosine theta? Well, it's got to be n sine theta. Why? Because the acceleration from this point is toward the center of the circle. The centripetal acceleration, this v squared r, is pointing in the positive x direction. So, and of course, we're then doing the second law. So the net force in the x direction is equal to m ac, which is equal to m v squared over r. Okay, the right side, left side is going to be n sine theta minus fs cosine theta is equal to m v squared over r. Okay, again, putting in mu s in for cosine, so 7 n sine theta minus mu s in cosine theta is equal to mv squared over r. Factoring out an n, but we could just put in n. I'm going to go ahead and factor it out because, and then substitute this guy in because I think there's going to be some, yeah, we're going to see some parallels. That's the easy way, I think, for me to do it. So from equation 7, yeah, this is going to be, I might be out of space over there too. You know what I'm going to do? I'm going to clean this up because I want to compare this new solution with these. I'm going to clean all that up and just erase all that. And I'm going to take this period because it goes with this and put it up here. So this was equation 13, and the period was equal to 2 pi times the square root of r over g times the sine of theta. And now I'm just going to, I don't need this anymore, so I'm going to erase that. But I didn't separate the board very well. We'll run out of space on that end over there. So I'm going to take this equation, and also, what did I do? Did I renumber or something? I did, didn't I? So it's 13. Let's keep it going. 13, 14, 15, 16, 17, 18, 19, 20. So now 21. This is going to be n times quantity sine theta minus mu s cosine theta equals mv squared over r. Now I'm going to substitute in that. Look what happens. I substitute in here, I'm going to get mg times, now the numerator is still going to be this thing, sine theta minus mu s cosine theta, but the denominator is going to be this thing, cosine theta minus mu s sine theta. And that equals m v squared over r. Almost done. So I get to cancel out a m here and here, multiply through by r, take the square root. And what I get is 23 mg times, all this is going to be in the brackets, I take square root, times quantity, sine theta minus mu s cosine theta over cosine theta minus mu s sine theta, quantity, all to the square root, all to the 1/2 power. Now, compare that to this thing. So this is V. This is V, I guess V min. Now, first of all, is it slower than this? Well, if I factor out a GR, it's kind of a little bit hard to tell, I guess, but I definitely, it definitely actually is not hard to tell at all, because if you look at the numerator, I've got GR times sine theta. Here I've got, oh, sorry, that's G, the M's canceled, that should have been R. But yeah, I still got GR times sine theta, but I'm subtracting something from sine theta. So the numerator here, like basically this is over 1. So this numerator here is definitely greater than that numerator. But then the whole overall number has got to be even smaller, because now I'm dividing it by something greater than, yeah, I think you could say that's greater than 1, because, well, yeah, I guess it's, technically it doesn't have to be, but I think it pretty much would be. Yeah. So I think probably safe to assume that it would be. Probably have to work it out first, though. But anyway, potentially we'll say that. But I think I think it would be. Now, I guess another way to, yeah. Actually, is that a problem? Because it should reduce to the same answer whenever the friction goes to 0, and it doesn't, because here mu s, that goes to 0, so that's sine theta, but then that mu s is 0, you're going to have gr tangent theta. And unless I missed something, that shouldn't have been the case. Or was it? Oh, dude, I think I missed something. This should have been, that should have been, it should have been tangent. I did miss something. I can see it in my mind now, right? Oh, y'all should help me catch that one. That was a silly mistake, because let's go back to that problem with restrictionless. I've erased the pictures, but yeah, that I think I must have been rushing, because this is the thing going around. Yeah, so this is the car. Yeah, I might have got thrown off maybe somehow when you asked me, because right, yeah, it's got to be tangent, not sine. Let's go back to this. So in the free body diagram, yeah, I probably missed that. That was just a straight up algebra error. So the free body diagram, what do we have? Let me just drop to here. I have, yeah. normal force there, and then I just have gravity. Yeah, it's got to be tangent. Because this guy, sure, that's going to be in sine theta, but this guy was in cosine theta. Yeah, in cos theta, and this guy was mg. So I just straight up missed it when I did the algebra. This is mg. So from the y direction, n was equal to mg over cosine, not just mg. And then in the y, so that, yeah. And so then we had in the y direction, we had basically n sine of theta is equal to mv squared over r. So when I substitute that in, the mg, n into here, it becomes mg sine over cosine, which is tangent. And then when you solve for the m's go out, you multiply through by r, so you have v squared is equal to g tangent theta. So v squared is equal to, so v is equal to the square root of g tangent theta. So my bad. I just, that was, but you see how that allowed me to catch the mistake. And I'm not looking, at any answer in any book. They got to match up. So somehow I missed that algebra in there when I was maybe going fast, but when I substitute that in there, it's not just mg, it's mg sine, the sine theta is there, then it's sine theta over cosine theta, which is tangent theta. So this is tangent theta here, and this is tangent theta here. Okay. So that definitely, going back to evaluate whether Vmin is smaller, it definitely is. Because, and now I can definitely determine that without having numbers. Because look, this is actually sine theta over cosine theta. So what you can say is that definitely this numerator is smaller. So if it's smaller, that is going to make Vmin smaller. But the denominator is greater. And so you're dividing by a larger number because you got cosine plus something. So it's definitely going to be larger. So you can definitely say without a shadow of a doubt that this Vmin is smaller than this V. Absolutely. So and then when mu is 0, it reduces back to this solution. Those two terms go out. Sine over cosine is tangent times gr and square root of that. So we're good. Yeah, we're good. We're good. Now, and the period is going to be greater because it's just going to flip. It's just a reciprocal, right? Because I'm dividing by that. So I guess we could put it in. It basically will be, I could write it down. The period, go ahead and do it since I asked you to do it. So I'm just going to write it. I don't think I'm going to have space over here. Maybe. So the maximum period is going to occur. Yeah, I need to erase this. I'm not going to have space to do that. I'm going to try to squeeze it in and can't get it all in. So this is going to be Vmin. So I'll box that in here. And Vmin corresponds to the maximum period. So T max is going to be, and that, you still get this 2 pi RG thing. So 2 pi times the square root of, and we'll have an RG in there just based on how I manipulated it before. So you can do that same thing. And now everything flips. So I'm going to have a cosine. Oof. Okay. Be a cosine of theta plus mu s sine of theta divided by sine of theta minus mu s cosine theta. And definitely this period is greater than that period for the same reasons we just mentioned, right? You break that into a sine over cosine, so you're adding. Sorry, this is cotangent. Sorry, that's if you flip it over, that's going to be cotangent. So cotangent because it flips over. Yeah, so you can kind of think about that. Now, that's for, what about V max? Now we don't even have to work it out. We can kind of extrapolate because these equations came from having, as Mike had told me earlier, having Fs be up the plane. But if it wants to slip up the plane, then Fs is going to be down the plane. And so every place you have a frictional term, you flip the signs in the equations. Look, if it's down the plane, then now my x component is going to be in the same direction as, so Fs, so that's theta, this is theta, so this is cosine theta here. And so it turns that component from negative to positive, and then it turns the y component from positive to negative, so Fs sine theta. So that's tantamount to just going through the equations, and wherever there's a term that has a coefficient of friction on it, because you know that's a frictional term, you just change the sign. So V max is going to be the square root of GR or RG times quantity sine of theta plus mu s cosine of theta divided by quantity cosine of theta minus mu s sine of theta. And you can go through and work it through for yourselves if you don't, just to convince you that that's true. And clearly, going back and checking the velocities, this velocity Vmax now is greater than the base, which it should be. And because the numerator increases and the denominator decreases, making the overall number larger. And then the period is going to decrease for the same reason. And not only is it, smaller than the max period, is also smaller than what I'm calling the base period when there was no friction. So T min is going to be equal to R over G. That term is 2 pi times that actually. 2 pi times the square root of R over G times, and just flipping the sign. So cosine of theta minus mu s sine of theta divided by sine of theta plus mu s cosine of theta. And yeah, sure enough, this is definitely going to be smaller than that because you're decreasing the numerator and increasing the denominator. Sure, and definitely smaller than this, obviously, as well. So I really like doing problems like that. These are kind of study problems because, you could see like I made a mistake, but then caught it because everything has to match a basic symmetry. Symmetry has to be there. And, yeah. Yeah. Any questions about that?
Wait, I have one question actually.
Yeah, go for it.
Remind me where you're getting like the cosines and the sines from exactly. Like, is it from the like the Fs times cosine theta and like the F sine thetas, or
It's from both the normal force and the friction. It's the same question you asked earlier. You see the normal force here? It's at an angle relative to the axis now. It's not along the vertical. This is the normal force. You see that? And the frictional force is also at the angle theta relative to the axis. This is the frictional force. So I have to find their components.
okay.
right? This guy is in, right? Because this is theta. The theta is here and here.
Right.
So this component here is n times the cosine of theta. And then n sine theta is this guy that's here. So mg is the only force that's along a coordinate axis. And there are three forces: the normal force, the frictional force, and mg. So the components, the sine and cosine, are associated with the normal force and the frictional force.
Okay.
And you can actually tell which is which just by looking at the form. I know it starts to look a little bit like Greek, but you can tell because the components that have the terms that have mu(s) multiplied by them, those have to be the components of the frictional force along the coordinate direction. So this would be friction, and this was the actually, well, let's look at the last solution. So this guy, mu(s) cosine theta, these terms are, this is the frictional force along the x direction, and this is the normal force along the x direction. I can see it from here. There was an n sine theta, and then there was an fs cosine theta. And the n kind of got factored out a little bit because, you know, it's mg, so it's related to other stuff, so things cancel out. And down here, this was the frictional force along the y direction, and this was the normal force along the y direction. It was positive in cosine theta, so the n got canceled out. It's the mg, the g is over here. Well, it got kind of canceled. It got canceled out and stuff that we did earlier.
Okay. I think what's confusing me, honestly, is like, I'm not sure if it's just me. I don't think it is, but like on like the top right hand side of like the board, it's like very blurry. Like I can barely even read it, I'm not gonna lie. Like especially like the smaller writing, like with like the greens and like the oranges.
Yeah.
Yeah, so those, yeah, I just couldn't
Well,
really like.
it kind of gets messy as we go along, and that was like the original drawing I did was larger. So do you have that in your notes? Because
Yeah,
that
I
wasn't
have.
the original.
Yeah, I had the original, but I don't think I had like I wrote down everything that like you had like what you just had up.
Yeah, well, you know, that the reason that
But
was smaller is because that was, I kind of did that pointing out small things and then just kept adding to it. The original one I tried to make clear and large, and but I don't have a lot of space, so I've erased that now. But
yeah,
that's where, like, that's if you didn't follow along with that, then I can see why it's confusing because that's where I started, and that's
yeah,
important, just like with all the other ones. So I don't know, like, we've done a couple problems. I don't know if, yeah, you know, it's you know, you have to kind of get that straight because it starts to add on to things as you move forward. But it's the same process that we've been doing along. So do you have one of them where it's clear? Because this was the second one I did. What about the one where the friction was up the plane? Did you write everything on that one?
oh yeah, I did. Yeah,
Okay.
I think yeah.
So can you go
I'm
back to that? So your question was, what is the sine and cosine? It's the same as that. So go back to that. When you
yeah,
go
yeah.
back to that,
I see
okay.
like the n sine thetas, like the n cosine thetas. So, and then where was it at? Yeah, like fs cosine theta. Yeah, and
Yeah.
fs sine
So
theta.
now, okay. So you see, so with that problem, if you take FS and flip it 180 degrees for when the thing wants to slip up the plane, just, you know, you can write that. So N doesn't change, mg doesn't change. Fs goes from pointing up the plane to down along the positive x-axis. So that's flipping it 180 degrees.
Okay, yeah, I see it.
So
I'm
what will happen? Go ahead.
Oh, I was just saying, like I'm just trying to visualize this now.
Yeah. So can you visualize that on your? You can redraw it if you want.
Yeah, yeah, I'm actually like drawing it right now.
Yeah. So it probably would be worthwhile for you and all of you, maybe because you haven't done it, you know, to go through and rework every little detail. But you can see just from doing that change, it's only going to make the components of the friction flip their signs. Because you're now going to have Fs cosine theta along the positive x direction as opposed to the negative when you flip it. Do you see that?
Yeah, because then if the car is sliding upwards, then the friction has to go the other way, right?
Yes.
Or I guess like if the car is slipping towards like the a negative x direction, then friction would have to go in the positive.
That's right. So its x component will be positive, whereas before it was negative. But now its y component, it being friction, the y component of friction will be negative as opposed to positive, which is what it was before. You see that?
Yeah.
So now, if that's the case, and that's the only change, and you didn't make any other mistakes, you can jump to the solutions that you had before and just go through it. Everywhere you see there's a mu-s, because you know that's the frictional term, just change the sign on it, and it gives you the answers for both the velocity and the period. Maybe do both, just because I've done it for you here. I didn't rework it. I just put the sign, but then go back and work it for yourself and make sure you get that answer. But you see that nothing else should change, so that's the only thing that should change in the solutions. Does that make sense?
Yeah, it does.
You sure?
Yeah, I mean, I even see it like where I just wrote down like the V min and V max are like almost exactly the same except for well a sign change. Like you just explained that. So and yeah, it makes sense.
So I know, I kind of I wasn't going as fast as I could, but I was moving through it. So in the end, you forget what we were doing. You forget like you asked me where they come from, and I know you know where they came from because when we talked about it before, like you were one of the ones that was participating, right? Because you asked me why the normal force, so I know you were paying attention. But that's just the way it is, right? Like it's kind of a lot going on, and it's not just physics; it's also trig and stuff. And you kind of have to brush on that. By the end of the problem, you forget what it was you were doing. That's why you have to work it several times. And I'm showing you all the details so that you can go through. And if you get stuck, if you can't, you have to do that. And then it starts to, you remember what I said. Some things make sense. Maybe you're writing too fast. You didn't think about it. Couldn't listen. You couldn't see what I was doing. These little details. And then you can go back to you have the video. So you can always go back and look at that. I know it takes time, but trust me, that is where the really good learning takes place. You go back and rework it for yourself, and then these things fall into place. But the short answer to your question is the sines and cosines come from the fact that we took the axis and we shifted it, because so that the x-axis is no longer parallel to the plane of the incline, but parallel to the ground. So that makes the normal force and now the frictional force have to be resolved. Whereas previously, when we did blocks on the plane, and even with the friction, that wasn't the case. That's where they're coming from. It's just that we shifted the axis. So it's like a transformation. It's like a transformation of theta. And we could do it from that point of view, but that's a much more advanced way to do it, looking at it as a transformation of the axis. And we don't have to do all that because it's just that's something else that we don't even teach in intermediate physics. Is being able, if you had a transformation of one axis frame to the next, you could take the answers and just go back and forth. But that's something else. But that's actually why. That's why. It's because the values of these answers will be the same, but they just look different because we shifted the axis by theta degrees for the reasons that I mentioned. Because using these kind of elementary methods of working out the problem, which are basically just algebra, it's easier if just the forces have components and not the acceleration. And if I kept the conventional axis, then mg would have components, but also even though it's just one force, but now because the acceleration has have components, then it becomes much more difficult to kind of get an analytical solution. That's why. So does that answer your question?
Yeah, it does. You know what? Actually, like I'm working like back towards like the equations I just wrote down, and
Yeah.
like I'm like starting to see like how we just like derive like like mu s cosine theta. Like I guess I was just writing this down too fast, like essentially.
I mean,
But
that's what class. I mean, that's that's
yeah,
all good, man. You don't have to. That's how it is in class, man. That's how it is.
yeah, I'll have to go back and
You have
work
to just
on
go
this.
back and
Yeah,
kind of
exactly.
redo it on your own at your own pace, writing little notes. That's what I did. Writing little notes, to what meant what, and just do it a couple times. After a while, it starts to bake in. Not just with this problem, but the other problems. You just have to, it's studying. That's how you have to study it. It's not memorizing the solution. You can't take this solution and then apply it to something else. It's going to screw you up. You can't, you just have to work through it every time and then you start to get faster. You start to see stuff. That's how you have to do it to really learn it. But what would frustrate me is that usually my professors didn't work out all these little details. They just left a little algebra stuff and it's just so at least I vowed that whenever I started teaching, I wouldn't do that. I would at least once work out all this, the details, um, so that and then now that we're recording it, so you have it. Ah, okay. Any other questions? Got 45 minutes. I mean, it's not bad to spend. I mean, I don't really have a problem. This is 4 days we've spent on Newton's laws for the 2 chapters. So this is probably the most we're going to spend on any topics. And they say 2 chapters. Honestly, when I first had this, we did it in 1 chapter. This is all in 1 chapter. So it's we're not behind. This is probably worth it. They start splitting them into several chapters because it's just so much information and so many applications. I want to do that one that I kind of saw there. That's a classic one. I actually have it in my notes to do sometimes as well. The one with the puck on the table spinning around. I want to do that one. And there's a precedence for that because it's yeah, it's you probably experimented with something like that as a kid with some toy or something like. I kind of do it right here, right? Let's say that I have some. This is a very light box. I think it was like 18 grams. This thing was more like 300 grams. So clearly, if you're just hanging them together, the larger mass is going to pull the smaller mass down. And that's why they have it there on the table. One mass. If it's a frictionless surface, definitely the large mass is just going to pull it down. So what causes it to stay? Well, centripetal force. Look at this. So when this thing so I've got a 300 grams here, maybe 18 grams here. No doubt about it, right? Like if you just, this is not a pole or anything. I guess, do I have something like that where I could put it through a pole, do it look like a straw or something? I don't think I have anything. Or actually, a friend of mine used to have a metallic straw. He gave me a metallic straw so to help with the earth. Do I still have that? Oh yeah, I do. I don't know if it's going to be worth the time to string this through. Maybe it won't take that long. I don't know if I can. Try real quick. Yeah, I don't know if it's going to string there. Oh, yeah. Yeah, I was trying to get started. Yeah, it's getting too. All right. Yeah, you know what? In that case, I'm just gonna. I guess I could put like a hook on it or something. Put the hook through this. That's a bit much. I have a small wire to do that. Well, I just have to kind of make do with this. You can definitely. I mean, your common sense is telling you that, right? That this is just right. If it's going to fall through, right? Yeah, you can see it there. Right, it's in my hand, but it probably falls. Okay, well, because common sense, right? Like the tension force, mg is equal to the tension, and the tension, if the weight is greater than the weight here, then the net force is going to be down, right? And this isn't even giving any resistance. It's not like it's on the surface or anything. You know, maybe you could say a little bit of drag, but in a vacuum, it's nothing, right? It's just, and there is no tension in the string, actually. Well, it is initially, and yeah, I guess it is because it's pulling it down. I mean, yeah, right. But watch, there is a situation where I could twirl this around, and you know, if I twirl it fast enough, not only will it not move down, it'll stationary. But if I twirl it even faster, it could pull this thing up. Watch. Look, I'm pulling it up. It's going up, right? Because this distance in string is decreasing. I know it's gonna whack somebody or whatever. Okay, so I'm gonna leave it at that. But you know, you get what I'm saying. You probably maybe you might have done things like that when you're a kid. I don't know. But that's something that I actually, you know, as a kid playing around with twirling things around that I could see. We did, you know, experiments like that which showed that kind of. So what is it? It's basically the fact that, you know, the tension force is created by the centripetal force in the string. And you can spin it fast enough because the centripetal force is proportional to V, right? And so as the speed increases, it's possible that you could have a centripetal force and therefore a tension that's greater than the weight of the bottom mass. And so that's what it's getting at. So let's take a look at that problem. And that's a class of problems as well, right? You could start with the frictionless surface, which is going to give you a baseline for period and for speed. And then when you add friction in, again, there's going to be a range of frequencies where it would slip in and the thing would pull it down, or where it would, you know, the speed be the maximum speed where the top puck would slip out and then pull the bottom mass up. So very similar to this kind of thing. Now, so I'm going to do that problem for you, and where we have the angle 0, and then show that, you know, it's somewhat similar in symmetry to these guys. Okay, so can I erase this right now? We good with that? Erase it. Don't need this anymore, do you?
Yeah, I think I'm good.
And I forget what number that problem was, but you know, you can look in the book. I mean, that's a classic physics problem. It's in all physics books. So you could probably even Google online and see a different explanation from a different point of view. Go to YouTube or something like that. Classic. Okay, so we have got the we have the table here. We'll do a side view and a top-down view. So the top-down view is probably going to look something like, well, it's the picture that they drew in the book. So you're going to have like Well, yeah. So I guess I'll do a side view, which looks kind of like this. Um, so you got the puck over here. We'll call it mass 1. Maybe I should make it bigger. Make sure you can see it. And here we have floor. So we have mass 1 over here. I'm going to exaggerate this. Now I'm not going to show any kind of pulley or anything, but I guess you have it going over that corner and some sort of frictionless deal. There's a string on it, and so we have a hole, kind of a hole in the table. The string goes over, it goes through the hole, and then holds mass 2. Let's say that mass 2 is greater than mass 1. So definitely if it's frictionless, everything's frictionless, it should pull it down. Now this is the side view. Based on this class demonstration, what we know is that if, for a certain speed, again, this is the hole here, mass 2 could be seen below, like if you could see it, I draw a dotted like that, it's going to be below there, mass 2. And mass 1 is right here, and it's being spun around, and it's holding mass 2. So it goes in and then just connects to mass 2 down to the bottom. That's what you see there. But mass 1 is speeding around at a, uniform circular motion like that. And at this point, its speed, v, is, going down. Like it's always tangent to the curve at every point. Right? So at this point, the speed is straight down, but the centripetal acceleration is always toward the center of the circle for AC here, and then here, AC, and here, and then here. All right? So that's his narrow. So the thing is, what speed should the mass 1 move such that mass 2 does not slip up or down, or mass 1, to the left or the right? I'll see if you can work on that. Just let me give you, and we got 30 minutes. So at what speed, so I'll write out the question so you have it in your notes. At what speed should M1 move such that, and this is frictionless, so we say that mu S equals 0, or just mu equals 0, such that at what speed such that no slipping occurs. Okay. Now again, with friction, just like with the car, you would actually have a kinetic friction opposite direction of motion, and there's got to be something, applied force in the direction of light. This could be like a remote control car or something like that. I don't know. That's attached to a string. But the force in the direction of the velocity and the frictional force, kinetic frictional force opposite that, they're not going to really affect our problem here because of the nature of the way centripetal force works. So I can acknowledge them, but I'm not going to use them for anything. So I'm just not going to worry about them. So it's related to the problem that we just, that we just did. Now on this guy, the other forces, I'm going to have the normal force up, which doesn't make such a big deal here. mg down, m1g down. And then the only thing I have in this direction is a tension force here. So that's the only force that's in the direction of the centripetal acceleration. And here, just two forces, tension up and m2g down. So it's a much simpler problem than the one we just did, but still has some of the same subtleties because there's no angle in there, right? So there's still some of the same subtleties. So see if you could apply Newton's laws in the vertical and horizontal directions. And I guess there's two horizontal directions, but here we can go ahead and put in the force. I don't like to not do something or put forces in. So here if it's moving around at a constant speed, then again, we would have to have an applied force out of the board, and we would have to have a kinetic frictional force into the board. Along the z direction. We don't have to worry about that. It's not going to affect us in the problem, but it's good to acknowledge it, so just so that we know that they're there, to acknowledge them. Okay, yeah. So see if you could kind of work that problem through, get some solutions there. Okay. Take a little break while you're doing that. Yeah. All right. So the X and Y, I guess Z directions also. Z direction, we're not worried about that. That's just going to say that the friction, the kinetic frictional force equals the applied force, and that's it. So whatever the engine force or whatever it is. So in the vertical direction or the Y direction, again, it's the first law. Also Y direction, and I guess I'm superimposing an axis like this, where. So I guess my axis looks like this. So Y up is Y axis, and to the right is the X axis. All right. So that the centripetal acceleration is pointing along the X direction. I'll put it up here. AC. Hopefully, is that too small? Hopefully, I'll make it larger. AC is pointing in the X direction. And again, this is a frictionless surface, so we'll say that from here, mu is equal to 0.0. All right. So in the Y direction, I just have N equals mg. Because N minus mg equals 0. So N equals mg. Okay. Trivial. In the X direction, the net force equals mass times centripetal acceleration, y, because it's going around. So that's just equal to mv squared over the radius. Well, I guess I didn't give you that. I guess I should. We would know that because that's this distance here. If you look at the side view, the radius is, you can measure that literally, is that distance. So that's r. And again, that's, this distance here. The way r. And so I'll rewrite the normal force over here somewhere. Okay. All right. So remember I told you the centripetal force is not some force in addition to all the other natural forces on the object that you would see. So it's always going to be the net sum of those forces. So in this case, there's only one, and it's the tension force, right? So the tension force is acting like the centripetal. In the previous problems, you asked about the sines and cosines, like we had various forces, a combination of friction and normal force that was on that thing that was giving rise to the centripetal force along the x direction. So that's how you have to think about centripetal force. It's never going to be a particular individual force. It's always going to be a net force giving rise to the resulting motion. So in this case, then, that means that the tension is equal to mv squared divided by r. Oops, I forgot to put that on r. Okay? And that's as far as we can go. Why? Because we don't know the tension. Well, with that, as far as we can go with that object, because we don't know the tension and we don't know the velocity, the speed. Now, notice also that in previous problems, anything can act like a centripetal force. In the previous problems, we didn't have a tension. We had, normal force and friction. And it also depends on how you set up the axis, right? If I had set up the axis like you said, I think you kind of asked this at one point, we wouldn't have had the normal force, a component of the normal force along the direction of, the acceleration. If you had set it up so that the component was, the x-axis was parallel to the plane. However, there would be a component of the acceleration in that direction. So, yeah. Anyway, now we go to block 2 to get the other thing. And in block 2, if it's not moving, there's no acceleration. It's not moving up and down, so we have the first law. So if we apply the first law to block 2, the net force, and I guess I'm going to do the same thing I taught you before. This tension in this case is in the x direction. So I'm going to swing this object over and make down the positive x direction for block 2. It's just the way I like to think about it. So that equals mass times. Now you might think, this is another thing to think about. You might say, oh, well, you said there was an acceleration in the x direction in this direction, but there's no acceleration here. Okay, well, how does that jive? Well, it's because it's not a linear acceleration. If there were a linear acceleration, then stuff would have to be moving. It's a centripetal acceleration. And so the string is not moving. It's not moving in the direction toward the center of the circle. It's moving perpendicular to that direction. So there's no motion, even when you consider it from this point of view in the x direction. There is an acceleration, but there's no motion. So when you translate it over, there's still going to be no motion in that direction. And you might say, well, is there acceleration? Well, because if it's along one direction, yeah, I guess you could say it is. I guess you could. Could you? Let me think about that. No. It's just the tension. Yeah, so this is how I explain that. That the tension force is acting like a centripetal acceleration in one direction, but it's not acting like a centripetal force in the other direction. How do you know that? Because of our thing I tell you, you have to look at the object and evaluate the motion first. The motion tells you what law to use. So that's really significant, because what I'm about to say, this is really where the physics is in the universe, right? Like, because we've never seen a situation like this, where we've had a certain type of acceleration for one coordinate direction that we define, but that acceleration is not in along the same coordinate direction for another part of the system. And that's just one of those things of the universe. It's true. That's what's happening. And because in one of the previous classes, when we were doing blocks on the plane, and we did have the linear translation, the linear velocity, moving over, there was someone in class, I can't remember who was, but they didn't really kind of jive with how I was doing it. And what they liked is they wanted to take the block 2, and this is the way it was, blocks on a plane. Take it and shift it up so that you can think of it moving along the x direction, just a horizontal direction. And I said, that's fine, you can do that. And that's because in that case, the acceleration was linear acceleration. So there was motion along every aspect of the x-axis. In this case, you could do that. I guess you could swing this up, but it's not moving. So you still have to have this thing kind of twirling around and this just sitting here. So it becomes like a mathematical I mean, it is anyway a mathematical construct, but it's like this thing would have to be twirling in on the part of the string that is part of M2, like going through it or something. I don't know. But this would still have to be twirling around. This thing would just be sitting there. So, you know, that's one place where that treating the problem like that still might work for the person, because you still could do it's you have to do set it up to describe whatever's happening. And it's not like, this is the problem with bias of measurement, bias in physics, but also this bias turns over into like socio-political this is where it comes from. Because if you've never seen something behave like that before, your intuition is that it doesn't make sense. But the universe doesn't work that way, right? It's like you don't project onto it what you think is happening just based on your personal experience. You might come up with something where it's not behaving in a way that you think, and you've never seen it before. So you can't just ignore it. You can't just say, well, it's not happening, or, you have to kind of consider maybe it is wrong, maybe it is not the way that it seems to be, but you have to consider all possibilities equally. And it's just hard to do that, right? But that's how you get these biases, bias in science, bias in, other aspects. This is a good example of it. So in this case, we've got a centripetal acceleration along the positive x direction, the way I'm handling, but when we come down here, it's not there. And why is that? That's the nature of centripetal acceleration. There is no motion in the direction of that acceleration. And also, why can you say it's not down here? Well, because that thing is not experiencing centripetal. It's not twirling in a circle or anything, right? So that's a little different, but that's what it is. That's what it is. And so there's no motion or acceleration in that direction. So it's the first law. So again, then you apply that T minus mg equals 0. So T m2g. So T is equal to m2g. So that gives me that unknown, and then I can take that and substitute it back into equation 4. And actually, by the way, this was m1. 1, 1, 1, 1. So when I substitute it back in, I get, 7 into 4, I get that m2g is equal to m1 v squared divided by r. So solving for r, I get that v, or solving for v. So I'm dividing through by m1, so I'm going to have basically g times r, and then I get a ratio of m2 over m1, and then I just take the square root of all of that. So that's the speed that I need, such that nothing moves, nothing slips. Basically, you got this ratio of masses, m2 to m1, where m2 is the driving, the object driving the system. All right. Now I want to challenge you. I would challenge you to then not put in friction. And there again, you're going to have, if it slips in, there will be a frictional force added here going out. And if it slips out, there's a frictional force added going in. So you're going to have, basically, you could kind of look at from the last problem, you're going to end up having this term M2. I think you're going to have like an M2 minus a mu M1 term, a mu M1G term, yeah, up in the numerator. And I don't think you're going to have anything in the denominator, but you're going to have that plus and minus up there. You should get something like that. And then maybe the next step was to then put block 1 on a plane, you know, and do the friction and non-frictional cases again. At any rate, that's how you study. That's how you learn. That's you don't have to necessarily do just the problem that they do, but like that's what I would do. That's what I did. That is to kind of just look at what I anticipate would happen. Once I had a baseline, I didn't need a solutions manual because I knew it had to reduce to the previous solution, and just going through and applying it every time and making sure things matched up with my intuition. That's when I really learned this stuff, right, and became confident in my ability to do it. So that actually went a long way in addition to doing, you know, a lot of the homeworks and, you know, doing, you know, keeping up with the work and stuff. So that's why I still like these and use these as a basis by which I teach all these kinds of problems. Anytime I would find like a family of problems, I would just kind of try to find like a baseline, you know, solution that's associated with like a kind of a baseline problem with that physical situation, and then start tweaking it, trying to make it more complex, seeing like I could anticipate how the solution would change, how the physics would change, and then whatever analytical solution I got, whenever I relax that change, it's got to reduce back to the other thing. So, and then, you know, I've even put this one on incline as well to see how it would change. Just playing around with stuff. So I think that brings us to the end today, 3 minutes. So in 3 minutes, any questions? So I would encourage you to at least go back in and put friction in. At least do that. And maybe if you're daring, maybe put this guy on an incline. Okay, and then you can put in some numbers if you want, I don't know. But you begin to see the symmetries and the patterns come out from it. Oh, I didn't do the period there. Let's go ahead and do the period. Well, the period we know is just going to be the 2 pi times the inverse, 2 pi r times the inverse of this thing. So the period for this guy, I can just write it down. It's going to be 2 pi times the square root. I'm going to get that r over g thing that I like, that comes out the way I write it. And then I'm going to have this flipped. So it's going to be m1 over m2. And that's going to be the baseline period. Oh, wait a minute. How did I get g in the denominator? Oh, yeah, because I got to take it, I divide through, right? The period is going to be 2 pi r over the velocity. So that's where it comes from. Yeah. All right. Any questions? I hope that helps you a little bit with these laws and centripetal motion in general. How you feel? Mikey, you're the only one that participated today. I don't think anyone else did.
This is just me. This is okay. For me, this is a bit more like involved than like what we did with like the other week with oh, what was it? Not the incline, the actually no, actually yeah, the boxes.
Yeah, I mean, I
I
get
don't
that.
know. It's just
It's
like
not. Go ahead.
like the idea of having like an acceleration while like something is stationary is like that especially is really getting to me. I don't know why. So I'm just gonna play with this. Like at this point, I'm just gonna do some additional reading, play with this more, and then hopefully it will soon. Hopefully, like hopefully I'll start to get it soon. Like actually understanding it, but yeah, that's kind of where I'm at.
Yeah, I get that. It's some subtleties associated with centripetal acceleration. That's true. But you have seen this, like even though I mean the confusion might be the description of it, but you have seen it before. Like I didn't really have a very good dramatization, right? I would have if I were able to put it through that straw. But you do know what I mean. Like you've seen that before where you'd have something furling and it will kind of can pull something up or something heavy can pull it down, right?
Yeah.
Yeah.
Like I feel like I've seen it before, like somewhere. Like it's not like it like blew my mind away when I saw it. It's like okay, well, I've seen that before.
Yeah, I'm trying to think of a practical example. I can't think of anything other than just like doing these little experiments like this, putting two masses together and then putting it on a straw or something and spinning it and see that. Yeah, yeah, I can't think of something practical where we see it, but yeah, hmm, yeah, maybe I should try to design something where that happens. But yeah, and this thing is accelerating M1, but M2 is not. So I think I kind of misspoke if I think I did say that, but or did try to correct it. But M2 is not accelerating; it's stationary; it's not moving. But yeah, this can have a zero acceleration, and this thing have an acceleration, and it is moving. It's just not moving in the direction of the tension. But that's also the case with centripetal. Like, hopefully, because look at, I mean, that you do know. It's probably just thinking of from a different point of view. That's what we've been saying the whole time. That the velocity for something, like even for this, that's the case, right? When this thing is moving around, if I look down at the circle that it's mapping out, this is a good diagram to explain it. Maybe I should go around this direction, right? Because you do understand that everywhere along the path, the velocity is tangent to the path. First of all, do you get that? The velocity is the direction of motion is tangent to the circular path.
Yeah.
You get that?
Yeah, I got that.
Okay. But I think you might have been the one of the people that told me the centripetal. So it is experiencing uniform circular motion, right? So that means it has a centripetal acceleration. And anyone, I think you told me or someone told me, but I think we've agreed that the centripetal acceleration is always pointing toward the center of the circle. So if that's true, there's always a 90-degree angle between the direction of the acceleration and the direction of motion. The object is never moving in the direction of the centripetal acceleration. That's very counterintuitive from linear acceleration, where the velocity is always going to be parallel to the acceleration or anti-parallel, negative acceleration. It's accelerating in an opposite direction of motion. That's when something is slowing down, but always along the same coordinate direction, either parallel or anti-parallel. So inherently, centripetal acceleration is very different than that. And because you have Newton's second law dictating the situation, because the centripetal acceleration is always going to be perpendicular to the direction of the motion, that means the net force that's causing that acceleration is also perpendicular. The thing that's causing this centripetal acceleration is not in the direction of motion. Very counterintuitive to linear acceleration, where if something is speeding up, the net forces are in, because that's when we did blocks on a plane, that's one of the things that we learned, that the acceleration is always going to be in the direction of the greatest forces. And the forces that are not, that are least are in the opposite direction, but still along the coordinate path. Centripetal acceleration, because Newton's law says that the net force, where is it? Well, I guess I've erased it, but here, the net force is in the direction of the acceleration. Even the net force is not in the direction of the motion. That alone, I mean, that's the same issue you're dealing with. It just makes it maybe a little bit more crazy because you're talking about two blocks. But from my point of view, the thing that is most nonsensical isn't the fact that it's two blocks. It's just with the one block. Just with even if there were no block there, like with this guy, that's very counterintuitive that the acceleration and the net force is 90 degrees to the direction of motion, right? So once you accept that, once that kind of sinks in as a characteristic of any kind of centripetal acceleration and centripetal force, then it's just kind of another, it's an additional step where you say, well, also, this thing has an acceleration and this doesn't. So up here, the tension force, which again is not, there's no inherent centripetal force. It just depends on the motion. So up here, tension and force is acting like a centripetal force. Down here is not. That is a little bit weird, but it's no more weirder than the fact that even when it does act like a centripetal force, it's not in the direction of motion. as compared to what happens with linear motion. So what I'm just trying to say is that once you start to get that centripetal motion is a completely different animal, which is why we give it a different name, it's not that much of a leap to say, okay, well, because we see it all the time, but we take it for granted. And the blocks down the plane, you've got forces, normal force and components of gravity, not giving the acceleration in the y direction, but then giving the acceleration in the other. Same thing is here. It's the same thing. It's just that it's a different acceleration. And also giving you it's the same direction because we define it that way. But that's what I'm saying. This is how the universe behaves. This is kind of how physics is, why it can get so difficult, right? Why you can have someone like Galileo being excommunicated because everybody thinks the world is the center of the universe. Right? Look up, everything's going around us. How could it not be? That's one of those types of issues. You have to kind of acclimate yourself once you start to look at the specifics of the physics and see how things can change around based on how you're explaining them. Things can be very weird and very different, but the weirdness is all around us. It's just that we get so used to it. And if you're not a physicist, you don't really have explanations for it. But when you start to look at the explanations and you see the contradictions and the breaks in symmetry, that's when you realize just how weird things actually are all around us. And so then you start to get kind of acclimated to that, to somewhat expect it, to somewhat, be kind of okay with it. But you have to test, to make sure, is this really what's happening? Is there an acceleration on this, but not on this? Okay, well, things work out. It's saying it, the numbers work out. When I measure, I'm getting the same answer. So I guess so. That's how science is. And so then you take that knowledge, it's now in your bag. And then when you go to the next thing, you're considering all these possibilities of how things might be. Does that make sense?
Yeah, definitely cleared up some like confusions I had, especially with like the centripetal, like I said, like the centripetal acceleration. That's the that's kind of hard to say. But yeah, like I just have to get used to the fact that like when a block is like or like for centripetal acceleration when like the a block is in motion that the acceleration index is perpendicular.
Yeah,
like that aspect I have to get used to, but yeah, like it makes sense though, and yeah, it did clear up some confusion I had.
I can tell you that's also why I don't. It's not that I don't like numbers. I should stop saying I do actually like numbers. Numbers are amazing, right? And for these geniuses who are good with numbers, they can see the patterns in numbers. I can't do that, but there are people who do, right? But for just at least at this level, because we get so we're trained, like we're trained in high school, get the answer, get as fast as you can. You're the smartest person in the room. Like this, I don't know, somewhere that starts back in elementary school, and it's just how I don't know. That has nothing to do with physics. That's not true. And you can get so focused on getting some solution and then feeling good because you got the same solution in the back of the book, and you have no idea what's going on just because you can plug numbers in the equation. This is the habit I'm trying to break because this is not physics. It's good engineering. It's good for the number crunchers, but what about the people who give you the equations to crunch the numbers? That's what this is. And so in order to make sure you understand what's going on, you have to derive the analytical solutions. And it's not just for the purpose of deriving the analytical solutions. It's so that you can think through and understand what is actually going on with the physics. And I know that it's new, it's new for you doing this, but trust me, this is as easy as it gets in terms of figuring out the universe. This is like 300-year-old physics, right? This is the easy stuff. The hard stuff is trying to figure out, like, how do you move through time? And what is quantum, like, that's where the cutting edge is. It's way beyond this. Related, but you definitely want to train yourself, if you're going to be a scientist, to be able to understand how to think. That's where the true value. This is why I do this stuff in class and don't use the numbers. So because you begin to see stuff like what just happened with you, Mikey, and then you begin to think about it and say, oh, okay, well, I got to get used to that. Yeah, that's like if you're just putting in numbers and getting the answer and checking the solution, you don't even you're missing all this stuff that matters later on. Not just in terms of this particular physics, but also the ability to think about it. That's the point. The ability to understand how sophisticated the universe is, even for small, simple stuff like this. The breaks in symmetry and what is happening. That's what gets more complicated. That's what, why we don't know what dark energy is and what dark matter is. That's why. And that's why it takes years to figure it out. Okay, I'm going to put my soapbox up right now, but I think that's good. I think it's good that this came up as a discussion and that you voiced that, because it is kind of like what? Like what? Doesn't even make any sense compared to what we normally think about. But then it normalizes once you think about it and you convince yourself that based on, again, just like they said in the Oppenheimer movie, you can be as smart as you want and come up with some beautiful theory. If it doesn't match with experiment, it's a bunch of crap. If it's the weirdest thing you've ever heard of and it matches with the experiment every time, then it's right. That's what dictates what's right. Does it match with what you're getting or does it not? End of discussion. And this matches. If you actually were to do experiments to measure you can see the thing is not moving. So clearly it isn't. And this isn't triple acceleration. It's giving the right values for the tension. So it must be what's going on. All right.
Yeah, sounds good.
All right. So class dismissed. By the way, I'm gonna go ahead. So we're done with this. We need to move on Wednesday. So I know I didn't post the test on Friday because I wanted to get some more stuff in here, do some more examples. But probably give you. I won't give you any pressure. You won't have to because I could post it I guess tomorrow. Have you turn in? But I'll just wait. The second test will be posted on Friday. You have 4 days to do. It's a 3-hour test. Turn it on Monday. I'll go ahead and post it now, and it'll open on Friday. And but we need to move on to. I think we kind of did. I kind of forgot. Had a kind of a long weekend. Had to travel, so we might have done a little bit of. Can't remember if we actually did, but I was going to do a recitation anyway. Another recitation, even if we did start and introduce work and energy. But I don't think we have. I think it was So we will do that. We'll start with work and energy. I guess chapter 7 on make some progress with that on Wednesday. I guess I can go back. I'll go back and check the video. I haven't posted it. That's why I don't remember. But if I did introduce things, which I might have, then we will start from where I left off with that introduction of work on Thursday, on Wednesday, last Wednesday. All right. All right. Well, class dismissed.
Thank you, Professor.
All right. Thank you.
Have a good.
All right. Take care. Have a good one. So, Arcadia, are you there? I think you sent me. Did you send me an email? I'll get to that. I think I saw. But are you there? I think I saw an email about some homework or something. But I'll get to that and give you what you need. All right. All right.
Okay, thank you, Professor. Have a good day.
Okay. All right. Have a good day.